remember that we use a confidence interval if we want to know what something is. So in this case, we want to know what the mean in the population is. So what is the mean height of all students at Calvin? What is the mean age of all residents of Grand Rapids? So we want to estimate what that truth is in the population, and we're talking about a quantitative variable. So as before, we start with our sample value. So before we start with a sample percent, now we're starting with a sample mean. That is our one and only and best guess at the true population mean. But we know that if we took a different sample, we'd probably get a different sample mean. And that's why we have to add and subtract this piece. This is the margin of error. The margin of error. It tells us how close we think this sample mean is to the population mean. So we'll start with the sample, add and subtract the margin of error, and we'll get this range in which we expect to find the true population mean. So how do we compute this? Well, this is the sample mean, the mean of our sample. S is the standard deviation of our sample. N is our sample size. So three things: mean, standard deviation, sample size, we get from the sample. So we take a sample, figure out how many are in the sample, compute the mean and the standard deviation, and we have three of the four numbers we need. The last number we need is a t-statistic, Now we can no longer use a z-statistic like we used for percents, because now we are estimating a couple things. We're not only estimating the population percent with a sample percent, that's what we were doing before, just estimating one thing. But now we're estimating the true population mean with a sample mean and the population standard deviation with a sample standard deviation. So because we're estimating two things instead of one, we have more variability. We have a flatter, more spread out distribution, the t-distribution, instead of the z-distribution. So we can no longer use 1.645, 1.96, and 2.576. So when you see a t, don't use one of those numbers. You need to go grab a new one from table T. And table T is on the flip side of your yellow sheet. So table T has something called degrees of freedom down the side. It has confidence levels on the bottom, and it has p-values on the top. So the degrees of freedom tell us, well, we get degrees of freedom from our sample size minus 1. Okay, so the t-statistic is related to sample size minus 1. So if we have a sample size of, say, 30, then we would have 29 degrees of freedom, and we would go here to degrees of freedom of 29. So when we want a confidence interval, if we want to find that t-statistic, we're just going to look up two things. One is degrees of freedom, the sample size minus 1, and the other piece is the level of confidence, which is here at the bottom. So we have options of 80%, 90%, 95%, 98%, and 99%. So if we wanted, say we had a sample size of 30, and we wanted a 95% confidence interval, we would just come to 95% confidence. Sample size is 30, degrees of freedom are 29, bring them together, and we would use a t-statistic of 2.045. So you just figure out two things. What are my degrees of freedom? Sample size minus 1. What level of confidence do I want? And then you bring them together, and that's the t-statistic you're going to use in your confidence interval. So I give an example here. Consumer Reports tested 14 brands of vanilla yogurt to determine the average number of calories in the population of vanilla yogurts. The mean of the 14 brands was 157.9 calories with a standard deviation of 44.8. Estimate the average number of calories in all vanilla yogurt with a 95% confidence interval. So we get the sample mean, 157.9 calories, the sample standard deviation, 44.8 calories, the sample size, 14 containers of yogurt, and then we need our t-statistic. Our t-statistic. With a sample size of 14, we have 13 degrees of freedom. So we go to 13 degrees of freedom. We want a 95% confidence interval. So 13 degrees of freedom, 95% confidence, and the t-statistic is 2.16. So we just plug in 2.16, the values from our sample, and we end up with a confidence interval of 132 to 183.8 calories. So we think the population mean is in there. not individual yogurts, not other sample means from other samples of yogurts, but we think the population mean, the mean of all vanilla yogurt, the mean number of calories of all vanilla yogurts is somewhere between 132 and 183.8. So we know our sample mean, 157.9. We do not know the population mean, but we think we know where to find it. We think we know where to find it. It's somewhere in that range. So based on that confidence interval, do you think it's reasonable to claim that the average number of calories in vanilla yogurt is under 100? Well, is 100 in the confidence interval? It is not. 100 is over here. So we do not think it's reasonable to claim that the average number of calories in vanilla yogurt is under 100 because our entire confidence interval is above that. We think the true mean is somewhere in this range, well above 100. What affects the width of a confidence interval? Is it this, 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 or some combination? Well, this definitely affects the width. Remember, that is affected by our level of confidence. T gets bigger as our level of confidence gets higher, just like Z got bigger, 1.645, 1.96, 2.576. T gets bigger as we increase our level of confidence. If you want to be more confident to catch something, you need a wider interval. So increase your level of confidence, increase the width. Standard deviation. Remember, standard deviation is a measure of spread, of variability. So if we increase our standard deviation, we have more variability, more spread, less precision. So if you increase your standard deviation, you will have a wider interval. Sample size. With an increased sample size, you have more precision. So we have a narrower interval. So all these things affect the width. They're all part of the margin of error that we're adding and subtracting. What does not affect the width at all is the sample mean. The sample mean only affects the starting point of our confidence interval, the midpoint of our confidence interval. So if the sample mean moves up or down, all it does is shift the confidence interval up and down. It does not affect the width at all, at all. Remember that we're not 100% sure that this interval contains the true population mean. It's possible that we started out with a very unusual sample mean and that this interval does not catch the truth. So we don't know whether or not it does. We just have to acknowledge that we're only 95 or 99% sure that it does. So there's a 5% or 1% chance over the long haul that our confidence intervals don't contain the truth. And remember that this margin of error, this piece that we're adding and subtracting, only includes sampling error. Sampling error, the idea that our sample mean is off from the population at random. It's going to be a little bit high, a little bit low, just by the sample we happen to get. But this confidence interval, this margin of error, this confidence interval does not include non-sampling errors, all those things that are caused by bias. So whether that's a volunteer sample or undercoverage or non-response or whatever. None of those things are included in the margin of error or in the confidence interval. So really confidence intervals are sort of optimistic because they only include one kind of error. The idea that this is off from the truth by a little bit because of the sample we happen to get. Let's see, outliers. Yep, outliers are a problem, and so we assume that we don't have any. Okay, and then interpreting this confidence interval. How do we interpret that confidence interval? Well, I gave 4 possibilities. 95% of all future sample means will be between 132 and 183. We are 95% confident that a randomly selected yogurt has between 132 and 183.8 calories. 95% of all vanilla yogurts have between 132 and 183.8 calories, or we're 95% confident that the mean calories in all vanilla yogurt is between 132 and 183.8. So which one is right? Only one of the 4 is correct, and it is the fourth one. The fourth one. We are 95% confident that the mean calories in all vanilla yogurts is between 132 and 183. The population mean, the mean of all vanilla yogurts, is somewhere in this range. The other 3 are all incorrect. The first one, 95% of all future sample means will be between 132 and 183.8 calories. Well, no. The confidence intervals for the mean of the population is not for future sample means. Other sample means will be close to the true population mean, whatever that happens to be. So it's possible that this sample mean, 157, is a bad one, just by sheer bad luck. But if we build our confidence interval around a bad sample mean, our entire confidence interval will be shifted up or down away from the population mean, and other sample means, very few of them will fall in that confidence interval if this happens to be a bad one out of sheer bad luck. So no, it's not true that 95% of other sample means will be in this range. It's also not true that 95% of individual yogurts will be in this range, or that we're 95% confident that a randomly selected yogurt has between 132 and 183.8 calories. Both of those are talking about individual yogurts. Individual yogurts are much more variable. So the mean is a lot more precise. Like we talked about in class, the mean heights in our classroom are very variable. But if you talk about the individual heights in our classroom are very variable. But if you talk about the mean height of our classroom, the mean height of the classroom next door, and so on, those are very precise. Those are going to be close together. So there's a lot more precision in means because the high and low values average out. So means are very precise. Individual observations are all over the map. So it is not true that we are 95% confident that a randomly selected yogurt has somewhere in there, or that 95% of all individual yogurts are somewhere in there. Those are going to be much more variable because individual yogurts have calories all over the map. It's just the means that are very precise. So confidence interval for a mean. The whole point is to estimate the true mean of the population. We use this formula, sample mean, sample standard deviation, sample size, and a t-statistic that we get from table T by finding the degrees of freedom, the sample size, bring it together. The degrees of freedom, n-1, the level of confidence, bring it together, and that gives us our T. We interpret it. We are 95, 99, 90% confident that the mean of the entire population is somewhere in that range.